Hey students, let me give a shot here to, let's see, number 33. It's from chapter 27. It's from the university physics book, which would correspond to volume 3, chapter 3, and it's number 39. And it has to do with either, well, double slit or triple slit. I'm not sure. Let's read it here together. It says, if a 500 nanometer and a 600 nanometer light illuminates two slits that are separated by this distance. All right, so this is the double slit experiment. So I'll just kind of make a little drawing here with two openings. Some light is coming. And what makes this one maybe a little bit harder is it's not just one wavelength, it's two wavelengths. So there's a 500 nanometer and a 650 nanometer entering the two slits. And the light's going to spread out. And what we learned is that if you have a single wavelength, now we have two wavelengths, and so let's have a discussion with that. But with a single wavelength, then there would be multiple places of constructive interference. And so if we measure from down the center, you can kind of see that this top opening travels a greater distance than the bottom opening. And if that's an integer number of wavelengths, so this, where m is either a 0, a 1, or 2, I guess you could even say plus minus 1, plus minus 2 if you call one direction positive and one direction negative. But if that extra distance, and this is the extra path difference, if you go through a little geometry, you can show that this extra distance here is d sine theta. So that's what we did in the lecture. And so we put together our wave properties and simply said that if this extra distance that one travels compared to the other is an integer number of wavelength, you'll get constructive or bright spots. And that's why you'll have a whole series of bright, dark, bright, dark, bright, dark. And you get it bright where this extra distance is either no wavelengths or one wavelength or two wavelengths or three wavelengths or four wavelengths. And then if it's like 2.5, then you get destructive interference. And so that's why you get this fringe pattern going bright, dark, bright, dark, bright, dark. All right, so what's going to make this problem a step harder is if you have two different wavelengths that illuminate it. So basically, we could say that we have this twice. We have bright, dark for the 500 nanometer, and we have bright, dark for the 650 nanometer. And so if we were actually looking at this on the screen, 650 is kind of a red, and so you would see a red pattern going bright, dark, bright, dark, bright, dark. What would 550 be? Let's see, the center green, 550. So I think we're getting really kind of a blue, maybe a light blue by this point. But Roy, oops, I missed the G. So that would be 550. Yellow's about 590-ish. Yeah, so we're in this blue indigo color. So a light blue to a kind of a royal blue. No, actually probably pretty royal blue. Yeah, 650, because that's 550. No, well, not sure what the color is, but I'll just call it blue. So hopefully what you would see is kind of a red pattern, bright, dark, and then on top of that, or underneath, however you want to look at it, you would have the blue pattern, bright, dark, bright, dark, bright, dark. And that's really the key to this problem, because it says here, how far apart are the second order maximum for these two wavelengths on a screen that is 2 meters away? Okay, so if you wanted to say, okay, what is the location, and I'll put an angular location of the second bright one of wavelength of 500 nanometers, it would be m equal to 2 times the wavelength, 500 nanometers, divided by the distance of the 2 slits. That's what the D stands for. So this is a half a millimeter. And then if we want to know the angular location of the maximum spot of the bigger wavelength, and you can kind of see, hopefully here conceptually, that angle would have to be a little bit bigger. This is the angle theta. Because you've got to give enough distance of 2 wavelengths, and these are bigger wavelengths. So we're going to get a bigger angle. So there's going to be some angle where the bright one for the blue is, the second bright blue one, and there's going to be some bigger angle for the second bright red one. And I guess it would look like this. Mathematically, you'd put a 2, you'd put a wavelength now of 650 nanometers, and you would divide it by your distance between the slits, which is a half a millimeter. So this would give our location here, and I'll call it an angular location, not the angle, or not the position on the screen. More on that in a second. Let me just check if I'm in degrees or radians. Okay, good. So I'm in degrees, and I'm going to, my apology here, this is actually sine of the angle. And so if I put this in, this is 2 times 500 nanometers divided by a half a millimeter. And so 0.002. And if I go we might be better off in radians, because let me just leave that as 0.002 for a second. That's kind of nice. And then let's do this one and save my little calculator work here. Let me just go back and copy that, because it'll be 2 times 650 nanometers divided by a half a millimeter. And so this is 0.0026. And the thing I like about radians is if you do an inverse operation, you get the same as the sine in radians, at least if you have small angles, and something under like a half a radian. And so we are. And so I would say this answer is not only sine of the angle, but it's equal to the angle. Now, the reason I kind of like that is because if we're looking the distance down the screen here, we could do something like this. If you remember kind of your angles from your trig class in radians, theta. This is an arc length, and then this is the radius. The arc length was defined, or really the angle was defined in terms of the wavelength by the ancient Greeks, but it would be the angle times that radius. Now, we don't quite have an arc, but we're pretty close, because this is 2 meters long here and only a half a millimeter wide there. And so you could think of this as kind of the flat part of a really big circle with a radius. But the point is, then, I could treat this straight distance on the screen about equivalent to an arc, and then I can use the angle in radians, and that's what I liked here. So I would say this, that the distance down, so I'll call it S2 of the 500, would be the arc length, 0.002, times this radius, which is the 2 meters that they write in the problem. How far is the screen away? And the same thing can be said about the position, the second bright one, for the 650. It would be 0.0026 times the 2 meters. In our question, oh, is my pen going out on me? All right, let me change pens here. Do I have another blue one? I don't have a nicer blue one. We got this blue one. I'll use a Bic. Okay. But now, if I want to know the difference between them, I'll just divide those in two and subtract. So this is 0.0006 times 2, which comes out to be 0.0012 meters.
Hi, Dr. Young.
Hope that helps.